Welcome to the Probability and Statistics course. Last time we talked about discrete random variables, and in this lesson we are going to see what continuous random variables are. We are going to see examples of continuous random variables and also what the probability density function is. As we have seen last time, we have our sample space, and the random variable x will take every element of the sample space and map it to a number on the real line. The difference from last lesson is that this time we are going to talk about continuous random variable. Let's see an example to see why continuous random variables are useful. So, assume that x is the height of a person in meters. We understand that the height of a person in meters can be given in any accuracy. So, for example, if we say that a person's height is 1.82, we actually have done a rounding. That means this number could actually be 1.821679 and so on. So we understand that we can have people in different heights, and it wouldn't be useful to ask what is probability of a person having a particular height. It would make more sense if, for example, we say what's the probability that a person has height 1.81 to 1.82. So we understand that for examples like this, it would be better to use continuous random variables. Let's go back to define the probability density function for a random variable. So the probability density function of a continuous random variable will be a function f such that it is greater or equal to 0 for every x in R. The integral of fx dx from minus infinity to infinity should be 1. And for all intervals a to b of R, the probability that x is between a and b should be the integral from a to b fx dx. Now let's see this graphically, what we mean. So here, when we talk about the probability of x being between two numbers, we actually mean what's the probability that we are in here. Now let's explain this a bit more. When we have continuous random variables, as we said before, there is no point in saying what's the probability of x being a particular number. So we would like to have an area. The probability of x between two numbers would be given. This integral is actually the area underneath this curve. This curve is this function f of x, and that's what in mathematics means the integral of the function. It is the area under the curve between numbers a and b. So by calculating the probability that x is between a and b, we actually calculate this area. The probability that x is a, as we said before, has no meaning for continuous random variables. So the probability that x is a for continuous random variables will be 0. And actually the probability of x equals to any number for continuous random variables will be 0. We are going to go through an example. Here we have x be the length of the next phone call in minutes. We assume that x has probability density function given here. We note that here the probability density function can be different for different x. So it's given by this formula when x is greater than 0. And in this case is 0 for x less than 0. Here we make a graph of the probability density function. So we see that the line, this line shown here, is our f of x. So probabilities will be given if we measure areas under this curve. Now we said that the probability density function must have some properties. Must be greater or equal to 0 and for every x in R, and the integral from minus infinity to infinity of f of x should be equal to 1. Let's see if this is the case for this example. Going back to our example, we understand that f of x, as we said, will be given, can be calculated by calculating areas underneath this curve. So we understand that this number will always be greater or equal to 0. It cannot be a negative number. The exponential here is always positive, and this number is positive. We understand this always going to be positive. Also, we are going now to calculate the integral from minus infinity to infinity of f of x dx for our example. In this case, we have that f of x is 0 from minus infinity to 0, and it is 1 over 10 e to the minus x over 10 dx from 0 to infinity. We can split here our integral, as we can see, in two parts as f of x changes between these two intervals. This is 0, and so we need to calculate this part. We can see that this will be minus 10 divided by 10 of e to the minus x over 10 calculated from 0 to infinity. And this will be this will be 0 when calculated to infinity, and this, if we put x 0, will be 1. So we can see that it is true that this is equal to 1. So we have seen that actually the function we have, it is a probability density function. Let's go back to calculate some probabilities. So, if we want to find the probability that a phone call will last between 2 and 5 minutes, we have to calculate that the random variable x is between 2 and 5. We note here that in the continuous case, it doesn't really matter if we include the equal here or not. It makes no difference in our calculations, as we have said that taking a specific value, the random variable x, its probability is 0. So the probability of x being between 2 and 5 equals to this integral here. From 2 to 5, the random variable doesn't become 0. We can just substitute x here. We substitute f of x here, and we calculate this integral. So, calculating this integral, we have that the probability that a phone call will last between 2 and 5 minutes is 0.2122. So what we had here is that we have the probability density function. We have the line here, and we wanted to calculate the probability that a phone call will last between 2 and 5 minutes. So what we have calculated is the area here, the area under the graph. Now we are going to work through an example to see slowly how we can calculate probabilities using continuous random variables. So, suppose that x is a continuous random variable with probability density function given by f of x equals a times e to the minus b absolute value of x. Now, if we look carefully at the probability density function and think about the properties, here x we allow to take any value in the real line. So if we think about the properties of this, we want this to be greater or equal to 0 for every value of x in R. We know that the exponential is always positive for b greater than 0. We have to assume that b is greater than 0. For this example, we are going to assume that this. And so we are going to require that in order this to be greater or equal to 0, we are going to need to have a to be greater than 0 as well. Also, we will need to check if the integral of minus infinity to infinity of f of x is 1, or it's better to ask when this happened, as we have these parameters here. We don't have numbers. Let's make clear that these are constants here, they are parameters. They could be any number we want as long as they satisfy these two conditions. We are going to find an extra condition here that should be satisfied, in order for this to be true. So let's do our calculations. We have that. I write again f of x, so we can have it here. And we calculate the integral. Again, we need to have this equal to 1. So we have that a, e, here dx will be equal should be equal to 1. Let's go on to solve this equation. So what we have is that this is a constant, we said. We can take it out of the integral. It doesn't play any role here. It doesn't make difference if we take it out. So you can have a times our integral and so this should be equal to 1 over a. This means that we are going to first calculate the integral. This integral, and then make it equal, let's put it here, 1 over a. We're going to see this part later. So we try to calculate this. We understand because here x, we know that this value is x for x greater than 0, and this is minus x for x less than 0. We'll include the equal there. In both cases it is correct. So this must be split down to minus infinity to 0, which will be e to the minus b. This will become minus x dx plus from 0 to infinity a to the minus b x. This is x dx. We see that 0 is included here and here too, but as we said before, it doesn't make any difference, as calculating the probability of x equal to 0 is 0. So we calculate these integrals, which are e to the bx over b plus e to the minus bx over minus b from 0 to infinity, and this will be equal to 1 over b. If we put where x 0, we find 1 over b, minus where x minus infinity, this will be 0, plus, again, if we put this infinity, this will be 0, 0, minus, we put 0 there, minus 1 over b. We can calculate this is 1 over b plus 1 over b. We have this is equal to 2 over b. So what we have is that 1 over a should be equal to 2 over b. So in order for f of x to be a probability density function, we should have that 1 over a equals to 2 over b. And thus, a should be equal to b over 2. This is our third condition. It should hold. We write the other ones here as well. We have a greater than 0, b greater than 0. We also see that from here it is obvious that if a is greater than 0, b is 2. So one of these conditions is enough. So now we are going to use our probability density function in order to calculate probabilities. If we ask the question, what is the probability of x being between 1 and 2, b in an interval. We said again, it only makes sense to talk about intervals. We have that. This is equal. Calculate the integral. Between 1 and 2. We have that. This will be minus b. Here we can use x, as x is positive between 1 and 2. And so this will be equal b over 2 a to the minus b x divided by minus b. We can quickly do these calculations and find out that this is equal to half of e to the minus b minus e to the minus 2b. Let's calculate another probability. If, for example, we have to calculate the probability of x greater than 3, what we mean by this, we again have an interval here. We actually mean the probability of x greater than 3 and less than infinity. Most of the times when we have to calculate probabilities like this for continuous random variables, it's better to write it like this. We leave out this part. This part is meant in here. So this will be equal, again, 3 to infinity of f of x dx. Again, we can calculate this integral, which is going to be p over 2 of e minus b to infinity to the absolute value of x dx, which this is equal to b over 2. We have this can be taken out of the integral. So from here, we calculate, and this will be equal to, this will be 0 if we put where x infinity, and where x 3, we get this value. So we see that b and b will cancel out, and so this is half of e to the minus 3b. If we're interested to find the probability that x is less than 3, there is no point, if we know the probability of x greater than 3, there is no point in doing the same work and calculating the integrals, as this we know will be equal to 1 minus the probability of x greater than 3. So this actually will be 1 minus 1 over 2 e to the minus 3b. So today we've seen continuous random variables. Last time we've seen discrete random variables. We understand that when in some cases we need to use discrete random variables when our random variable takes values, takes numbers from takes discrete numbers, and when our random variable takes values, continuous values, then we need to use continuous random variables. So we have seen last time and this time random variables, when to use random variables, several examples. In this particular lesson we learned about continuous random variables and how to calculate probabilities using continuous random variables. And we've seen the probability density function. For more information on this lesson, you can visit the web page of UNINETTUNO MedNetU project.